As usual, I'm gonna wait for 1 minute. Okay, so let's get started. So can everybody hear me? Would you say yes if you can hear me? Okay, so thank you very much. Okay. Okay, so where we are. So here's a quick reminder about what we have done so far. So we have been studying simple imperative language. And then so far we talked about, we defined the syntax, and then also we developed enough tools to define its meaning, which is called domain theory. So in the domain theory, it's in a sense a theory which let us specify good space and good functions between spaces. So spaces that features in domain theory are so-called predomains. And then there are something called the domains. And good functions between them are called continuous functions. And we looked at them because the continuous functions allows us to, continuous functions allows to say something called least fixed, have a least fixed point theorem. By the way, later we're gonna use another result from domain theory, which also incorporate the ideas from category theory. That's called the recursively defined domain. So that is something that we're gonna look at later. Okay, so using what we developed so far, we were in the middle of giving the semantics of this language. And I said the key part of the semantics is about specifying the semantics of types. So what that means is that in our language, we have three non-terminals. One is called integer expressions. And the second is called Boolean expression. And then the third, so this is int x, Boolean expression. The third one was a command. And then by giving the semantics of type, what I meant is to specify what this interpretation function should look like, what's going to be the target set, or target space of this interpretation function should be. Because that clarifies what kind of, in a sense, that identifies the property of expressions, Boolean expressions, commands that we have in this language. So the integer expressions, it was the mapping from state to integers. For Boolean expression, it was a mapping from state to Boolean values. So command, it was a mapping from state to state lifted. In all cases, we can put C because when we consider all these sets like sigma, integers, Booleans as pre-domain with a discrete order. Okay. Now, as I said, this semantics identifies the key properties of this language. The properties are these expressions and Boolean expressions always terminate, do not have any side effects, and commands potentially can diverge, so that's why we can have a bottom, may go into an infinite loop, but that's the only thing. So it doesn't raise any exceptions or doesn't do anything strange. Later, when we extend the language, which fundamentally change the characteristic of the programming language, then the interpretation function has to be changed. So you can kind of see for any changes in the language, you can kind of decide whether the change is really substantial or not by looking at the interpretation function. If it requires the target space to be different from what we have right now, that means that there is some fundamental change in the language. Okay, so actually we looked at, I said this the first two, similar to, essentially identical to what we studied before when we looked at the language for integer expressions and the language for predicate logic. The last bit, the third one, is something different. But we looked at its interpretation function, and the interpretation function is defined in a syntax-directed way that is, in a sense, quite intuitive. So therefore, in semantics of, say, skip, it's just skip doesn't do anything. So if you take input state sigma, so that sigma comes from this input sigma, then we have to return either sigma or bottom. In this case, it's just return sigma because it doesn't do anything. For assignment, it takes state and it updates state such a way that variable x now has the value of the expression. And then sequential composition is really the sequential composition we studied, but we have to be sequential composition of C1 and C2, but we have to be slightly careful because when you run the first command C1, it may return bottom, which means that first C1 may go into infinite loop. Then the entire thing has to be infinite loop. In other words, the interpretation of this second guy has to map bottom to bottom. The first guy doesn't terminate, the entire thing doesn't terminate. So we do it by doing this lifting, which we discussed when we talk about the lifting of construction for predomains. And then if then else is really just if then else. C2, say that if the evaluation of a Boolean is equal to true, then we run C1. Otherwise, we run C2. So this is what you expect. Now the last bit, which is a bit unusual. That unusual thing is the while loop. So semantics of while, B to C. here we use the tools from domain theory. We are saying we apply the fixed point operator on this space, sigma to sigma bottom, to a functional f that we're gonna define. And then this functional f will be a mapping that takes sigma to sigma bottom. So continuous map, put continued here, from here to sigma bottom. And then this y compute a fixed point of this continuous function, capital F. And then for once we have a fixed point, that's going to be some element that maps sigma to sigma bottom. So we just put the initial state sigma. So applying this fixed point operator gives the meaning of the while loop, and then so that we can apply that meaning to the input state sigma. So then the question becomes what's going to be f? I said the f will take, let's call it g. So g is an element of mapping from sigma to sigma bottom. Then it takes state sigma prime, and it does the following. If it essentially models the one unrolling of the loop where G represents what's going to happen after one unrolling. So if we say we evaluate Boolean condition on the sigma prime, if it's true, then we do something, otherwise we do something. But if it's false, then one unrolling of the loop, say that if the loop condition is false, we have to get out of the loop. So the output state is going to be just sigma prime. Otherwise, we go into the loops and we execute body of the loop C once to sigma prime. And then we run the rest of the loop again to the outcome of what we have here. But then I said G is going to model the loop after one unrolling. So this G lifted is something that we have to apply. So that's the definition of the while loops. So what I'm gonna do today is that we're gonna do today first is we will look at study the interpretations or maybe justification of the semantics. Say semantic interpretation. And this is semantics, especially the one for while. Okay, so why this is the correct definition? So that's the question we want to answer. So one way to think about this is to think about the intuitive equality, the term equality that we are expecting. So if you have a while loop, P to C. So this is intuitive equality. I'm not saying this is a formal equality, but this is what we expect. So if you have a while loop, we expect that if we unroll the while loop once, that meaning has to be the same. Okay, so that's what I told you when I talk about this chapter. And in fact, this is a kind of either optimization or program transformation that people do often when they think that this is useful in the sense that it may speed up the program or it may clarify some of the things that's going on in the program. That's because people expect this equality to be true, and it actually has to be true. And then this interpretations of F, this is semantics of a while, actually coming from this intuitive equality. So first, this intuitive equality say the semantics of a while has to be a fixed point of this capital function F. And so say this one essentially says the semantics of a while should be a fixed point It doesn't tell us it's a least fixed point, but they say it should be a fixed point of f, capital F. Okay, why that's the case? I mean, I'm not going to go all the details here, but I mean, the main reason why this is true is the following. If you take the same if then else, but we change instead of while here, we say we have some other command C prime. Okay, C prime can be anything, and then we write as a skip. We ask what's going to be its semantics. Then it turns out if you just use the semantic definition that I just gave you and do some calculation, this semantics is exactly the same as f applied to meaning of C prime. Okay, I mean, if you really do the calculation based on all the things that's given here, I mean, well, actually without including while, so all the things for the first 4 cases, then you can actually get this equality. So equality follows from this definition. Okay, what does this mean? It does imply, this means that now if you look at the right-hand side of this equality, the right-hand side is the semantics of if then else, and where C prime is equal to while. So this right-hand side, the same meaning as F applied to semantics of while. And then if you look at the left-hand side, underline the right-hand side. If you look at the left-hand side, this left-hand side should be, if you take its meaning, it's going to be while B to C. So this intuitive equality that we say tells us this right-hand side, and then we just call it left-hand side. And this left-hand side should be equal. So that's what this intuitive equality say. So the intuitive equality, if we believe that has to be true in our semantics, so our semantics has to justify this intuitive equality, that tells us the semantics of while has to be a fixed point of f. Okay? So then, so that answers the first question. So it say, okay, our interpretation of while, using it as a doing it as a fixed point, it makes sense because that's what we are forced to do if we expect this one loop unrolling optimization is correct. But then the next question we can ask is while list. We may say, okay, it can be any fixed point. Why should I choose the least fixed point? And here's an intuitive, I will give you one example, and then we first talk about intuitive reason. Intuitive reason is that using lists boils down to saying, unless forced by loop unrolling, the meaning of while at input state sigma should be bottom. What does intuitively mean is that loop unrolling really means describing the behavior of a loop exactly at 1 iteration, 2 iteration, 3 iteration, and so on. So taking the least fixed point really corresponds to saying, if this loop unrolling tells us what the output state has to be, then we say that's going to be the output state of the while loop. But otherwise, we're going to say the output is going to be a bottom, which means the loop is not going to terminate. And that intuitively, I mean, that if I rephrase it in a different language, that means that if loop terminates, unrolling really means executing loop once, twice, 3 times, and so on. If loop terminates in an intuitive sense and produces certain output, and that's going to be the result in the least fixed point. If your loop does not terminate, then in the least fixed point, it's going to be interpreted as a bottom. So bottom corresponds to non-termination. So that's what this least fixed point let us have. If I go it a bit more formal, let's look at one example. So here's the one loop that goes on forever. So you always go into the infinite loop. You always go into the loops, doesn't change anything. So then it's intuitively we think that this is the program that fall into the infinite loop all the time. But now we can ask, okay, what the semantics tells us. So if you take this semantics, it's going to be this y operator applied to some capital F. But it turns out this capital F, which is a mapping that takes sigma to sigma bottom to sigma bottom. It turns out this F is an identity map. If you put a G, it returns a G. And here's a calculation that allows us to see this. So if you have a F, then if a G, then say that the meaning is if under some input state sigma, say if a Boolean condition true, evaluate as sigma, if that's the case, then we run G lifted after running skip sigma, otherwise just return sigma. Wait, this is true. But true always have a value true, so this is always holds. So this is identical to say G lifted running skip on the sigma. But skip we said is an identity function, so that's the same as G lifted and sigma. And G lifted, if it's given user state, the same as G sigma. So we have shown that Fg applied to sigma is identical to G applied to sigma. So that entails F is an identity function. F of G is equal to G. Okay, so it's an identity function. What does it mean? This means that everything is a fixed point. Okay, so every G is a fixed point of F. Okay, so which means that the least fixed point is going to be the mapping. So the least fixed point is going to be a mapping that takes sigma and return the bottom that correspond to our intended meaning of this while loop. I mean, this while loop always go into the infinite loop. So this least fixed point exactly mirrors that behavior. This is G is a least fixed point. This G take any state sigma and go to the return bottom, which reflects the original program going to infinite loop. But if you take a different G, but non-least, but fixed point, so this is G1, G2, which takes sigma and returns sigma. That's a program that terminates and returns sigma. That's not the intended behavior of this while loop. Okay, so what this G2 does is that it, in a sense, manufactures the outcome, the output state, which is not forced by the loop unrolling. So loop unrolling in this case doesn't tell us anything about what output state should be. So that's why this the first case, any state is going to be mapped to bottom. But this non-least fixed point actually does this kind of, incorporate this artificial outcome. So that's why we have this strange behavior. Okay. More formally, in the textbook, it explains what's going on in this way. You can define a sequence of program. The first program is called, let's say, omega 0. that's always go into the infinite loops. While to skip. So, I mean, this is the context of where we are interpreting the command while do C, okay? So we are interested in the semantics of the while. And then in the textbook, we write it as W0, which go always into the infinite loop. W1 is the same as these while loops up to one unrolling. So you'd say if B, then the program first runs C. So if Boolean condition is true, we go run the body of the loop. But afterwards, we run W0, otherwise skip. And then W2, say B, then C, W1, otherwise skip, so on. So each of Wn model is a bit, in a sense, similar up to while loops. For states, I mean, for which the loop terminates at, I think it's a less than n iteration. So each Wn is an approximation of this while up to, for all states which make the loop terminates up, I mean, within the less than n iterations. Okay, so that's okay. That's the, in a sense, syntactic approximation. But what one can show is that each of these Wn, if we take its semantics, that is identical to the capital F. So this F is coming from this semantics of these while loops. Capital F iterate. So it's the same as the running, applying this capital F to the bottom. So bottom is an element in sigma to sigma bottom. So this bottom is a function that takes state and always return a bottom. Okay. I think because I'm using bottom many, maybe you may get, I hope you don't get confused. This bottom here and this bottom below are different. The one bottom is a function above in the function, bottom below is something which is at the same level as a state. Okay. So that's what can happen. So that the least fixed points, so the least fixed point of F is really for, I mean, by the least fixed point theorem, it's a least upper bound of this chain that is the same as least upper bound of this Wn. And then one can show that, I mean, one can argue, I mean, this least upper bound of Wn really means we are really modeling the behavior. This really means that we are thinking about all the finite executions of possible finite executions of the while loops. If finite execution doesn't tell us anything, which means that the loop go into the infinite loops, so it doesn't terminate, then it's going to be a bottom. Okay. So this one can intuitively be argued that it has to be the meaning of the while. I feel like I didn't really explain well about this third part, but my point is that this f of n corresponds to this syntactic approximation of Wn. Once you accept the semantics of a while, is essentially covered by, is really least upper bound of this syntactic approximation. So this is syntactic approximation described while exactly at its limit. So then you can accept the meaning of the while loop has to be the least fixed point. Okay, so that's a bit more, in a sense, meta-analysis or meta-justification about why this semantics works. And now I want to solve some exercise. So let's go back to the semantics. So exercise I want to solve is this. Try to use this semantics. So use the semantics to prove the following. E1 to sigma, same as x and y. Swapping the order of command, y e2, x e1, sigma. Well, let's erase this. Show that these two things are equal. If x doesn't really appear as a free variable e2, y doesn't appear as a free variable of e1, and x and y are different. So I'll give you 2 minutes to solve this problem. Okay, so here's a way to solve this. So then if we just pick any state sigma and do some calculation, we write it below. So we compute x gets e1, y e2, apply sigma, and by the definition of sequential composition, this is same. It's the same as y becomes e2, lift it, apply to x becomes e1, apply to sigma. Then if we do the calculation of the argument, it will be sigma where x is going to be mapped e1 under sigma. And because the entire thing is a state, the whole thing will be sigma where x gets evaluated under, it gets mapped to e1 sigma, and y gets mapped to a little bit complex. So I gets mapped to right, E2, the semantics of E2, where E2 gets evaluated under sigma updated. Do some cleaning here. Okay. Right. So E2 is evaluated under this state, which is a state input state. Now, one thing we can do here is that we know X and Y are different, and also variable X doesn't appear in E2. Okay, so because variable X doesn't appear in E2, by the correspondence that we talked about when we study integer expressions and also predicate logic, what's true is that this E1 sigma and Y E2 sigma is true. Okay. Then furthermore, because X and Y are different, we can change the order. I mean, this change order like this. Sigma X E1 sigma. Okay. Now, if you do the similar kind of a calculation for the other command, X becomes E1 sigma. So then we end up with having this E2 sigma. Here we again use a correspondence, but with respect to E1 instead of E2. Okay. So we are using correspondence with respect to this guy. So instead of sigma, here we have something more complex, which involve the updated value of Y, but we can replace it by sigma. That's because E1 doesn't contain the variable Y. Okay, now you can see these two things are equal, so that we are done. So that's how we can answer questions like this. Very simple, but it shows you one application of semantics, which is to show justify certain equality, which often becomes the basis of compiler optimization. Okay, so let's move to the next topic, which is, oops, I think we have, this is 2, 3. So the next topic is the local variable declaration. So we're going to now extend the language in two ways. Extension. So the first extension is a local variable declaration. So here we are introducing a new syntax. So we have a command. And then this command have all the user cases that we talked about before, and it has one more. We say we declare local variable new var, which should be a variable that should be initialized by some expression. And then this is an integer expression. And then in the body, we have a command. Okay. So it turns out having the local variable doesn't really change the language fundamentally. In other words, it changed something, but it's not really fundamental change, like adding exceptions to the language. So one consequence of this is that our semantics of this local variable declaration doesn't really change the interpretation of types. So the semantics of command will remain the same. So our interpretation of a command will still be a mapping from state to state bottom. Now here's an exercise I want you to do. I think all of you have a good idea about what local variable declaration should look should mean. So based on your understanding, define the semantics of new var variable x becomes as an expression e in the command C. So what the right-hand side should be. So fill in the right-hand side. I'll give you 1 minute to do so. Okay, so the meaning should incorporate the following idea. You first say we initialize variable x with value e, and we run the command C. But one thing that you might have missed is that we have to restore the original value of the global variable x. So this x here is a local variable. So when everything is done, the name x should be bound to the original global variable. Okay. So these are the 3 steps that needs to be done, and here's how you can do it. So we first update sigma so that variable x, local variable x, now has the value in its initial value. Okay. So that talk about this initialization part. Now what we have to do next is we have to run command C. So we run command C. So if you just write that much, then that's not enough because this x is a local variable. So at the end of the execution, we have to restore the value of global x. Okay. So how we do it? So what we do is that we run the command with transformation from state to state bottom, which take state sigma prime, and then it returns sigma prime, but it changes x to the value of x at input state. So this is the value of the global variable. So we take state sigma prime, and then we change its binding for x so that the x has the original value of the global variable. But this command C may fail to terminate, so we have to write this lifting so that if the original commands, the execution of this body of new variable declarations leads to divergence, so the entire thing should lead to go to the infinite loop. Otherwise, we do the value restoration by running the command, this transformation here. And now, so that's the definition. But once we have this local variable declaration, then we can define the notion of a free variable appearing in the command C, also, which is defined just like what you expect. It's defined as usual in the syntax directed way. If I give you just a few cases, so defined. defined in a syntax-directed way. And a few cases are if we have a free variable of C1, C2, so free variable of C1 union free variable of C2. And if we have free variable of variable X and the assignment, so free variable of expression union assigned variable and so on. So the definition is pretty straightforward, except that one has to be a bit careful if we have to talk about new variable in C. Then this has to be a free variable C where X gets excluded. But we have to take the union of free variable of expression E. So that's what we have to do. And then, but in the, so this is, in the imperative language, there is another concept, which is a free assigned variable. This means that all the variable appearing in C that gets updated by some command inside the C. We don't care whether that command really get executed or not. We just collect all the variable that appears as a target of assignment inside the command C. So then definition is also syntax directed. And this you can think of this as a very simple effect analysis, a program analysis. And it's very straightforward. Free variable C1, C2, free assigned variable. It's a free assigned variable of C1 union free assigned variable of C2. But for assignment is different. Instead of collecting free variables of E, we don't do it. We just return X because X is the only updated variable here. And then the local variable is essentially the same, u bar X E in C, because we only care about free variables. When we compute free assigned variable, we get rid of X. But then anything appearing in E are not updated. So that's it for the free assigned variable. So then you can define the rest in a syntax directed way. Okay, so why we care about this then? Once we have this free variable and free assigned variable, we can prove certain theorems like a correspondence, which plays quite important role when you analyze when you do some theoretical analysis of this language. So here's a lemma. So this is a correspondence lemma, which roughly speaking, if you are running some program under two states, which say exactly the same thing for all the free variables, then the outcome should be essentially the same. So that's what this lemma is telling us. So we have a command here. And then we have two states, sigma and sigma prime. States state in sigma, but they satisfy the following condition. The conditions say, as far as command C is concerned, they are the same. So what does this exactly mean? For all variable W, which appear free inside the command C, sigma and sigma prime say the same thing. Sometimes some people write something like this, that sigma is equivalent to sigma prime with respect to the free variables of C. Okay. So they're saying sigma and sigma prime are the same. If that's the case, then following thing happens. Yeah. So it has a two-part. The first part say, if that's the case, then either C, if you run C under sigma and run C under sigma prime, they are the same and they equal to bottom. So they both diverge, or they both terminate, sigma prime, both in sigma, and they continue to satisfy this relationship, which means that as far as free variables of C are concerned, this sigma and sigma primes are the same. So C W, same as C, sigma prime, for all free variable of C. So that's the analog of correspondence lemma. We didn't have this complicated conclusion in the correspondence lemma for integer expressions and predicate. In those cases, we just said they are equal. But here we have some complication. That's because of the possibility of divergence. And also the outcome is not a single number or Boolean, but an entire state. So that's why we have this complicated conclusion. But intuition is the same. If command is given two states, which are essentially identical, which are say the same thing for all the free variable in the command behave the same way with respect to these two states. The second one is about free assigned, the assigned variable. Say that we have again commands, and then we have a state sigma. But in this case, suppose that when we run command C, the state sigma, it's not equal to bottom, it's a state. So if that's the case, what happens is that for variable W, which is not assigned by some assignment inside the C, input state, output state say the same thing. And this is also what you expect. If command is not updated, then they should say the same thing. But using denotational semantics, you can actually prove this. We are not going to prove this, but these are the two properties. So it tells us how this free assigned variables in C, free variable of C are, affects the influence the semantics of the command C. And there's another lemma, and there are fewer lemmas in the book, but there's another lemma, which is, this is a kind of a lemma. So this one is a useful one that perhaps you may want to use when you solve a homework exercise. And it can be used in many different contexts. The second lemma is more like, again, justification about why our interpretation of this new variable is okay. What we are expecting is, if our definition is correct, the exact name of local variable shouldn't really matter. And the second lemma say that's the case. It's a renaming lemma. So what that tells it, here's what it tells us. If we have a command, if we have this variable w, new, the x becomes e inside command C, that has the same meaning as new y, e, and C, where x gets replaced by y. If variable y doesn't appear as a free variable of C minus x. So if we just replace x by x, it doesn't matter anything to change anything, so it's okay. But as long as y is, it doesn't really appear as inside C, we can always do this renaming. So that intuitively tells us the name of local variable. It's actually new var. So here, name of local variable shouldn't really matter. Right, so what we did so far is that we extend our language with this local variable declaration. And I said that it doesn't fundamentally change the language, which you can see it by the fact that the denotational semantics of a command type doesn't really change. And also our interpretation of this new var makes sense because it satisfies this renaming lemma in some sense. Now, what's the other way? There's actually another way to kind of extend the language. Very common other way is called syntactic sugar. This one. So the idea is define a construct as a background. So we define something, and then the definitions, the in a sense preprocessor of the language will change our new language construct into something that already exists inside the language. So here's some attempt of so some attempt that we can do. I mean, the simple things that we can write is if we just write say twice of C. So this can be defined, syntactic sugar, as just running C twice. Okay, twice is a new language construct, but it's defined in terms of existing language construct. Of course, this type of construct won't change the fundamental nature of the language because after all, everything can be expanded to the existing language. But this type of constructs will make programming a lot easier in many different contexts, in many different applications. So it's commonly used in the language design. So often what people do is that they define language, the core language, and then once this core language is defined and many other much richer features of the languages are defined in terms of syntactic sugars. So here's one exercise I want you to do. Suppose I want to define syntactic sugar for loops, okay? So I want to define for construct, which is say for variable x, it gets initialized e to e1 up to e2, and then do the body c. Okay? So that we want to define this as a syntactic sugar, and I want you to do this. Okay, how we can define it as syntactic sugar. So let me tell you a few things that one has to be careful. The first, here's the faulty or some problematic definition. So suppose we write for x e2 to c like this, say that we assign x to e1, and then we run the while loop where x is less than, until x is less than equal to e2. And then we, in the body of the loop, we run c and increase x by 1. So that's one possible definition. What's the problem with this definition? The problem is that now x is a global variable. So after, if you do this expansion, after running this for loop, the value of the global variable x will be changed. Often that's not what we intend. We intend that the intention is we want x to be a local variable defined inside only for this for loop so that it doesn't influence the value of global variable x. So that's not incorporated into this definition. So in the exercise, think about this issue and try to define the definition of for loop that avoid this issue and some other issues that you can think about. I'll give you 2 minutes to do so. Okay, so the answer here is that we define it like this. We declare new variables, but it's a bit tricky. We declare new variable w. Let's instead of w use y. New variable y, and that gets initialized with E2. And then we define another new variable, x, that gets initialized to E1. And then we run while. Then E2, no, then y. And then body is C with x get increased by 1. And then reason we, so the reason we declare this local variable x is exactly the one that I told you. We don't really want to update the global variable. And here y is fresh. So y is a new variable that doesn't appear anywhere. And the reason we use y is because if E2 upper bound happen to contain variable x, we don't want, I mean, if E2 is something like x plus 2, we don't want this x here, the local variable, the index variable x, to be the same. The x on the right hand side is you look at the value of the global variable. So that's why we evaluate upper bound before running anything and store it in a fresh variable y, and then use it as an upper bound. So that's the definition. And lastly, if the one want to define this for loop as intended, they may also want to impose another condition which say this C, the free variable of C shouldn't really contain x. So x shouldn't really appear inside free variable of C. That's because sometimes this for loops is just intended to say we want to execute this C up to certain, we want to execute C certain number of times without really making C access the index x. So this type of a condition can be imposed in the definition. So the point I'm making here is that syntactic sugar is a very simple concept, but one has to be careful. If you define in the wrong way, then this syntactic sugar has an unintended behavior. Okay, so what's now it brings us to the last bit of the last things that I want to talk about this chapter, which is the soundness and the full abstraction. So we have 3, 4. So you can say quality of semantics. So how can we measure this? So we defined the denotational semantics. I gave one approach, but there are some other approaches of giving denotational semantics. Something is based on so-called predicate transformer and so on. So one might wonder why the denotational semantics that we gave, which is something that we can trust. So here's the piece to answer that question. So in many times, the study about programming languages is to formalize some informal question into a formal question so that we can study about it using tools from mathematics. So for the denotational semantics, we can say, okay, why this semantics makes sense. And the programming language researchers came up with some concept. So the concept is something called the soundness and full abstraction. So the soundness, to talk about the soundness and full abstraction, people often define some intuitive notion of equality between two commands, okay, C and C prime. And this is defined separately from the denotational semantics. Okay? And then we said our semantics is a sound if two things, C and C prime, have the same meaning. So then C and C prime are equal intuitively, or equal with respect to some other notion of equality. And if that's true, then we say the semantics is a sound, which means that we can use the semantics to do compiler optimization. Okay, if you prove certain compiler optimization preserve the denotational meaning, that can be employed to in practice without changing the meaning of the program, intuitive meaning of the program. So this implication from the left to the right is a sound. Implication on the other direction is called fully abstract. So if the implication the other direction is true, then we say the semantics is fully abstract. I mean that this coming up with the fully abstract semantics for a rich language has been a big open problem in programming languages before, which is reserved around 90s by multiple people in the UK. Okay, so these are the two key concepts. So then the question becomes, how can we define, this notion of intuitive equality? And here's some tools that people use in PL, which also appears in some form in mathematics and some other area quite a lot. This is so-called observational equivalence. So somehow my notes respond very slowly. Okay, so how does it, so this is about formalizing this intuitive notion of equality. So how we do it? So we identify two things. One is so the one is a set of observable phrases. And the second is that a set of observation. So a set of observable phrases with a whole, with a single whole. And then we specify a set of observations. These are the two things that we specify to formally define observational equivalence. And a set of observation phrase with a whole is sometimes written like C, and it's also sometimes called observable context. And then, so this set of observation is written as a O. And these observations are typically mapping from commands to Boolean values, like true or false. So this means that these observations, if you give a command, it does something, it maybe run program or does something, and then return either true or false. So this intuitive equality say, for observational equivalence, C and C prime, let's call it O, this is observably equal. If and only if, for all context C, in this C, and for observation O, in this O, if we, so the context is observable phrases in our case. I'm gonna give you a specific example it's essentially a command with one core inside the command. So if you, for this context C, if you fill in this command with the C1, the context C, if you fill in with the C2, and apply this observation, these observations should be identical, okay? What does this mean? Intuitively, this C means that use case of C1, CI. So C, C is like a surrounding command that command that surrounds this command, this small command C1. And plugging C1 and plugging C2 means that we plug in C1 or we replace C1 by C2. So these are the two different different instantiations of the context with the different commands C1 and C2. And then now this observation O means that, observably, the person who are using the C1 inside the big program capital C won't be able to tell the difference between whether we are using C1 or C2. So in the picture, I have about 3 minutes. Then in the picture we have say this big command. So this is a big command C, and then we are asking if we can plug in this hole with the C1 or plug in this hole with the C2. And then we can ask whether it's going to make any difference at all, observably. And then the observational equivalence that do not really make any difference at all. So it's called observational equivalence because we talk about observation. This O and C are all about this some form of observation of this command C. And here's concrete examples. And that's going to be the end of today's lecture. Is given like this. So we can define the context C to be, so it's actually the context which is parameterized by two commands C1 and C2. It's going to be all the program command with one hole where we new var C var xn kn, and then it's a big hole. Then finally we have if xi equal to k, then skip else diverge. So where this is a command with one hole here, and then this k1 up to kn, okay, they are all integers. And then this x1 up to xn, this is exactly the set of free variables of C1 union free variable of C2. Then I is one of them. Particularly, choose one of the particular variable. Okay. So the context, what I wrote as a C here, is the same as this entire thing. This is equal to C. And we are plugging in this specific command C1 into this hole and specific command C2 into this hole, and see that whether they return anything, make any difference at all or not. For the observation in this case, we can choose this. I mean, this is not that ideal observation, but you can just observe each of the observation should be a mapping from command to Boolean value. So say that if we run this command C in our semantics on the sigma 0, if it's a bottom, then true. Otherwise, false. Where this is, yeah. So we can just have a single observation like this, where the state sigma 0 is a state that maps all the variable to value 0. Okay. This is not typically what people do. Typically, for the observation, they run it, they use the operational semantics to specify the particular mapping, but this is one definition we can give. So with respect to this definition, we can ask whether our semantics is sound and fully abstract. And I think it's sound and fully abstract, although I don't have any proof. Okay, so that's it for today. And as usual, I'm gonna be here for 5 minutes. So if you have any questions, you can ask me. Okay, so thank you all for attending today's lecture.